interested either in the theory itself or in the applications, which are really I mean, you cannot number them. Okay, you cannot number them. As I told you at the beginning, just myself, but I'm only one. Okay, I have papers that go from black holes and quantum and the microwave cosmic background to muscular dystrophy, passing through the development of smart sensors for companies who live on patents. Okay, passing through, I don't remember because I have too many collaborations. And then it takes time. So, but if you are curious, I can tell you. It's not, the story doesn't finish with what I'm telling you. It hasn't even begun. Okay, we are before the beginning with what I've been telling you here. Okay, we haven't scratched the surface. But to know that there is a surface is better than not to know. Okay, so, and of course you have your own backgrounds, you know how to do a lot of things without need of using my tools. There is so much more in the world, okay? So I don't even want to say that this is absolutely important for your future career or whatever. Okay, you take a glimpse. It's something that maybe doesn't happen too often. And as my grandmother used to say, because it is a saying of my country, impara l'arte e mettila da parte, which means learn the skills and put them in a safe place. Okay? Because once you have the skills, you never know. Maybe one day. Okay? So, with this much, let us... and then what I want to say is this. I have seen some of you a little worried about the content and things, much as I try to reassure you that it will not be, the exam will be easy and so on, although it has to be done. That in the last hour, whatever I have covered now, which is short, and in the second hour, in the last hour, we may just have, for good part of it, half an hour or more, I'll see, just a free discussion between us. Okay, now I also sit, you don't only sit. If you have questions, curiosity, or things, I try to give you my view. Okay, so, for the time being, let us continue what we started. Sivaraji, because we started late, you tell me when I have to stop. If I have to stop at 11:30, right, then I stop at 11:30. Can I have the full hour? Yes. If you like, it's not, okay? Okay, so anyways, now I continue with this part. And let me remind you quickly which was the last thing that we wrote that we wrote last time. So we had this. We had that a probability density about a certain value z of some random variable at a given time t plus tau can be expressed as an integral over all possibilities of a so-called transition probability p of z at time t plus tau, given that we started in z prime at time t, okay, times the probability at time t of being in z prime, which is w z prime t dz prime. Okay, this is the probability, the elementary probability of being close to z prime at time t. Now you combine that with the transition probability, and you get the probability density at time t plus tau in the point z. And this becomes a definition of P. You don't have to ask yourself how difficult it is to prove that equation. No, it's not equation, it is a definition. Okay? Oh, by the way, now that I see you, some of you, right, reminded me that in my previous class, I told you that a measurable function is a function that maps measurable sets into measurable sets, but maybe I was tired, because it is the inverse, no? It is always the pre-image that we are interested in. So it is measurable if its inverse maps measurable sets into measurable sets. Okay, so I wanted just to say this because it was a mistake that I had. So anyway, we said things can be written in this way. Now for P, we have written an expression. Okay, after we introduced the characteristic function. Now I don't repeat the whole thing. Okay, I just go straight to what we need. We have that P of z at time t plus tau, given that it was in z prime at time t, okay, this could be expressed as an anti-Fourier transform of the characteristic function, which is this. 1 over 2 pi integral from minus infinity to infinity for variables that are only one-dimensional of e to minus I u z minus z prime that multiplies 1 plus sum in n from 1 to infinity of iu to the n divided by n factorial, okay, of the moments of the transition probability, mn of z prime at time t with an increment tau, okay, and this has to be integrated in the Fourier variable u, du, okay, where the moments of P, mn of z prime, t, and tau could be expressed as the integral from minus infinity to infinity of z minus z prime to the n times the probability density of which you get the moment. So P of z t plus tau given z prime at time t, okay, integrated in dz. Okay? So I think we came to this point. Now, as I told you, look, if you read the books, maybe even if you listen to some lectures, maybe they don't make clear this fact that so far we have done nothing. Okay? But we spent a lot of time in class. We have done nothing. Because we have only tautologically rewritten things. Okay? So far, we have nothing in our hands that can be used. Okay? But as Gauss, the great Gauss, used to say, to look at the same problem from a different perspective is always useful. So, by rewriting things and doing nothing, we have, however, provided a different point of view on the same thing. Okay? So maybe we can use it. Yes, in this case we can use it. We are not always so lucky, okay? But sometimes we are lucky. So what do we do? In here, we have this product of P times W. Okay? Now we have an expression for P. This P was unknown before, it is unknown now. Because here it is defined through Mn, which is defined through P. So if you don't know P, you don't know Mn, and you don't know this. That's why I'm telling you we did nothing. But watch out. Watch out. Let me write P times W. P of Z T plus tau, given Z prime at time t times W of Z prime at time t. This will be equal to this right-hand side multiplied by W. Okay? So it becomes 1 over 2 pi integral from minus infinity to infinity of e to minus I u z minus z prime. Now bracket. We take this inside the integral. Okay? So it becomes W of z prime t because you see here we integrate in du, okay? So I can take it inside the integral. W z prime, which goes in place of 1, plus sum in n from 1 to infinity of iu to the n divided by n factorial mn of z prime t tau that multiplies w of z prime t, okay, and all this integrated du, okay. The w, because depends on z prime and t, can stay equally the same inside or outside the integral, doesn't make a difference, but if I write it inside the integral, it becomes more interesting. Okay? Now, in my notes, there is the explanation. I only give you the result, and you may also be aware of it, okay? Without any need that I tell you. But there is one expression of the Dirac delta function, delta of x, as a Fourier transform. Okay? 1 over 2 pi integral from minus infinity to infinity of e to the I kx dk. In which sense this is equal to this? In the sense of operators. It means that if I apply the linear operator defined with this delta of x to a certain function space, then it is the same as if I stick my function inside the integral. Okay? And what do we know about delta x? We know that its integral, that the integral of a continuous function, it has to be at least continuous. Okay? The integral of a continuous function with the measure that is delta x dx is equal to the function in point 0. Now, you think, and if you stick the function here, you get the function in point 0 if it is continuous. Okay? In my notes, in any case, there is the direct derivation. So let's come back to this, having this in mind. Because now you see, you have some stuff that you can treat as a delta function. And so, if we write w of z t plus tau, which is the thing we would like to know. What is known in this equality here? What is known is the probability at the earlier time. That you have to know. okay? Because even if I say I drop this pen and thanks to gravity it falls to the ground, that is an equality. But to know how it falls to the ground, I have to tell you what is the initial condition, how high it starts, and also if it starts from standing still, like now, or if I throw it up and then gravity pulls it down, or if I push it down. So the equation is still the same, but the initial conditions make a lot of difference, and without knowledge of the initial conditions, you cannot go anywhere. So we have to know that. But if we are lucky, we do an initial measurement, we do some initial operation, and then we know the initial situation. That is what breaks that vicious circle of going around and knowing and going from knowing nothing to knowing nothing. How do you break this vicious circle? By the knowledge of the initial condition. Because now you know something. Now you know a little. Maybe little, but with this little knowledge, maybe you can do something. Now look at this as it is written. Okay? I can express it in this way. I can express it as integral of w z prime t, which is the thing that I have inside this integral here, times the delta function evaluated at z minus z prime dz prime. Okay? Which is the first piece we have here. You see? The 1 over 2 pi integral from minus infinity to minus infinity e to the iu z minus z prime. Okay, you see, you get the delta at x. If here I stick z minus z prime, I get the delta at z minus z prime. Okay, so now I have this times this. Okay, the w inside or outside the integral makes no difference. So this is what it is. Okay. And then I have plus. Now, look at the next term. Okay? In the next term, you have n equal 1. You have n equal 1, and then you have iu. Iu to the n, iu divided by 1. You have iu. If you look at this expression here, that is the derivative of the exponential. That brings down a minus iu. But here I have a plus iu. So this thing becomes plus, but actually minus, derivative with respect to z of the integral of, here you have m1, because we are at n equal 1, so you have m1 of m1 evaluated z prime, t, and tau, okay, times w of z prime t, okay. Now, because I have done this derivative, I'm back to have an exponential, because the exponential doesn't change when you differentiate it. It only pulls down the constant factors you have in front. So I still have a delta function. From this, that multiplies this stuff. So again, I will put a delta z minus z prime dz prime. Okay? IU, m1w. The IU, I get it by doing the derivative with a minus sign, because here there is a minus sign. So I have got the IU. All the rest is m1w, and then I have 1 over 2 pi integral of the exponential. It is a delta function, like before. Okay? So that is what you get. I just do you continue like that. The second step will have the second derivative, because you will have IU to the second power. So you bring down minus IU a second time. Minus minus gives us a plus. But now look at the structure of this integral. The structure of this integral is the product of m1 times w times the delta function. This evaluates these functions in z prime, evaluates them at z. So see what you get. You get from this w of z t, which is our initial condition, the one that should be known, what I have at time t, plus, which is a minus, d by dz. What is that? This is the moment. This is the moment that multiplies w. So you have minus d by dz, m1 of z, because now we are there, t and tau, times w of z, t. And the second term, well, the second term will be plus. Now you have 1/2 because you have 2 factorial, which is 2. Okay? 1/2 second derivative with respect to z. Second derivative with respect to z of what? Of m2. Of z t tau that multiplies w. Now you know how to continue. Okay? Now this thing is already something. Now we are out of nothing. We have something because we have assumed that we know w at time t. But you can reach time t from time 0, so you know the initial condition. Why this is something? Because on the left-hand side you have your unknown function at time t plus tau. But on the right-hand side you have the known w. You have the known w. So if you could in some way compute m1, m2, and all the following ones, now you can get the solution that you were looking for. So the question is, can now we get a little further? And I wouldn't be here if we cannot, right? Can I, what do it? Ah, here. Beautiful. Now use the right pen and try not to drop it continually. Pen is already selected. Okay. Now let's do something. Let us write this quantity. W of z at time t plus tau minus w of z t and divide by tau. Okay? So if I do that on the left-hand side, I have to do that on the right-hand side. If I take the limit for tau goes to 0, this is equal to limit for tau that goes to 0. Sorry, that comes after. This, of course, is equal to dw by dt evaluated at z and t. Okay? But is also equal to limit tau that goes to infinity. And now we do the same trick on the other side of sum in n that goes from 1 to infinity. Now we lose this. We lose this w because we do minus w. Okay? So sum in n from 1 to infinity of 1 over n factorial minus nth derivative with respect to z of, what have we left? We are left with mn of z, t, and tau. We have divided by tau. Okay? And we still multiply w of z and t. Okay? So now the question is if I can evaluate this limit for the things that depend on tau. If I can get some expression for the things that depend on tau, which is this ratio. It is this ratio. Now you know, the story now gets a bit involved. But if you follow, if you have any book on stochastic processes, okay, and there are many, and I told you some of them, or if you have a chance to attend a course on stochastic processes, then they will show you that for a number of interesting cases, in fact, it is possible to give an explicit expression to the limit of mn divided by tau. Okay? But this becomes, has to be treated on a case-by-case basis. You give me your stochastic process, and then we will look at the expressions of this limit. Okay? Now there is a very famous theorem by Pavula that is almost as old as I am, but not that much. 1967. Okay? So it is a fairly old theorem, but I'm quite older than that. And that gives us a very useful hand. Yes? Here? The limit goes inside. No, the rest are like constants, no? I don't know, maybe I don't understand the question. Division by tau. Ah, sorry, 0. You're right. Yeah, you have to... Ah, eraser. It doesn't care much. I do select. You're right. Must go to 0. Okay? Now, this theorem by Paula, what does it tell you? It tells you this, that this equation that is named after Kramers and Moyal it is called Kramers-Moyal expansion. Why an expansion, it is clear, right? This Kramers-Moyal expansion can only have 3 cases, okay? That it stops at n equal 1, because all the other terms are 0. This is the case of deterministic dynamics. Okay? If you go to the program, it says that at some point I give the connection between stochastic and deterministic. Okay, if it stops at n equal 1, you are in the deterministic case. Because what you get, I will write it later a little more explicitly, is the Liouville equation. The equation that we treated in the lecture before the last. Okay? So you are in the deterministic case. Or it stops to n equal 2. This is the case that people actually normally use, to which the so-called Fokker-Planck equation, that now I'm going to tell you what it is, belongs, or it doesn't stop. All terms will be different from 0. Okay? So this is a deterministic case. This is a stochastic case in which there is a deterministic part, something that looks like a deterministic part and an added diffusion process. And this is the most general case that nobody wants to treat, because it's very complex. It is very complex. Now, in many situations, what people can do is to say, yeah, this thing goes to infinity, but if we truncate at a sufficiently large n, we get it sufficiently good. Unfortunately, it does not work that way. If you are in case 3 and you neglect some of the terms, say from high order to infinity, because you think you have got good enough, no. As time goes, probability densities can become negative. They can become negative, but probabilities cannot be negative. What is the probability that this afternoon it rains? Minus 0.5. Have you ever heard something like that? No. Negative probability is something we don't want even to think about. Okay? Please. Other 10 minutes. Yeah, but if it becomes too heavy, I'm happy to stop earlier. The only thing, I need to go to the restroom 1 second. So but I come back right away, yeah? Try to finish a little earlier. Okay, so these three cases, 1, 2, and 3, is what the theorem of Aula does. Now, if any of you is familiar with the notion of cumulants, of cumulant expansion of a probability, then it is the same thing. Okay? If you have a probability, you can express it in terms of its characteristic function that I gave you the other time, which is defined in terms of moments. But a more useful notion is that of cumulant. I don't have the time to go through that. If you know, good. If you don't know, never mind. Yes. Yes. Thank you. Maybe captured anyway what I was saying. So the expansion of a probability density in terms of cumulants that are related to moments, by the way, through a formula of a famous mathematician from Turin. Again, Fa di Bruno. Okay, he has a very important formula in combinatorics and number theory, and he was from Torino. So cumulants and moments are connected to each other. Actually, Fa di Bruno wasn't the only one who had in mind that kind of formula. And so there is always a little bit of friction, you know. No, it was my formula, no, it was his formula. In any case, I think that mostly you find in the books about Fa di Bruno, and someone else gets a little angry, but like Liouville is credited for an equation that he didn't invent. At least Fa di Bruno invented his own formula. If also someone else did it, okay. So the formula says that the cumulant expansion can either stop at first, second order, or go to infinity. And it is the same thing. Okay? It is the same thing, and you could guess that it is something of that kind because the moments are related to the cumulants. But now, let us look at a case in which all this stuff easily makes sense. And that is in part implemented in the MATLAB codes that I gave you for the tutorials. Okay? It is the Langevin equation. The Langevin equation, which writes like this. You have z dot equals a certain function of z and t, h, plus another function g of z and t, times what is called the white noise, gamma of t. What are the properties of white noise? The properties of white noise are these, that is a stochastic process. It is one of those random functions that you don't know which values they take, but you know that they have certain statistical properties. And the first property is that E expected value of gamma at any time t is equal to 0. Which is easy to obtain because whatever process that has got an average, you obtain the process that has 0 average by shifting it by the average. You subtract the average and you get 0, because average is a linear operator. Okay? And then its correlation function at different times, E of gamma at time t times gamma t prime is equal to delta. Actually, if you want to make calculation a certain way, it is 2 delta t minus t prime. This is all what you know. This is all what you know. You know that average is 0 and correlation is, as you call, delta. Is a delta correlated process. What does the second property mean? The second property is very important. And then the result is what is called the Langevin equation. Which is the most popular of continuous time stochastic processes. You find it everywhere. I use it, for instance, to describe the motion of bacteria when they search for oxygen. Okay? But people use it for almost anything that you can think at a small scale, at the nanometric scale, at the scale of nanotechnologies. You find a lot of this. And bacteria are larger than that, but they have certain properties, okay, that also seem to be describable with a kind of Langevin equation. Of course, there are variations of this equation that are much more complex, but the idea is always this. You have some kind of systematic part in the sense that it is known what it is, and you have something that is unknown, or better, is known only at a statistical level. And if you have this delta correlation, then you are in that same field of the Langevin equation. The rest is computational difficulties, if you like. What does this thing mean? What is a correlation? Well, as the word says, it is a kind of causality connection between things. Okay? The sun shines and I get a tan. Not as much as Sivaraji does. He's a little more tan than I am, even if he doesn't get any sun. If I do, I get a little more similar. But we are still brothers, so even if not too similar. So you see, there is a correlation between the sun and the color of my skin. You understand that, right? But it's not like placing a camera on a comet, where there is more than correlation. There is causality. If I shoot the spaceship with this direction, this velocity, it will end up on the comet. While if I'm exposed to the sun, maybe I don't get the tan. Okay? It happens. It happens. Of course, this is more evident in many things. For instance, they tell you that if you smoke, you have a high probability of developing lung cancer. But the case of very old people who have been strong smokers all their life are known. And often they are brought in by tobacco producers and cigarette producers to say, you see, it is not true. No, unfortunately, they are wrong. Because, yes, some people escapes that fate, but nevertheless, the vast majority of people get their lungs damaged, and then it is bad. And then it is bad. Okay? Same problems for living in places where there is too much pollution. It's like smoking. Say, do you smoke? No, I don't smoke. But you know, I live in a healthy environment. Maybe pollution or maybe some other reason could be radioactivity, which is also found in the ground or in some. Okay, so these things have to do with correlation rather than with causality. So, what is the meaning of this correlation here? The meaning is that correlations decay instantaneously. Because this thing, in a sense, in quotes, is different from zero only when t is equal to t prime. For the rest, the correlation is zero. Are there processes that are like this? Well, to a certain approximation, there are processes that are like this, processes in which the memory of what comes first is lost practically immediately. But there are many phenomena in which correlations are not lost immediately. Let me give you an example that I like, because in the science festivals in Torino that we have to attract students to the science subjects, okay? We do it throughout Europe, not only in Torino, but it's an experiment that has been done various times to impress young people and encourage them to enroll. You take water and you put flour on it. You make a pool, okay? Big pool with flour in water. Now, if you step inside the pool like this, you reach the floor immediately. But the chemical substance is starch. But if you don't do that, but you do this, you can walk on water. You can do it, okay? Go to YouTube and find the videos of people walking on water, and then they stop and they sink. Okay? Isn't that beautiful? You know what is that? That is the effect of persistence of correlations. What happens is the following. If you put your feet down slowly, there is time for this mixture of water and starch to move away from where it was. So there is time for water to forget that it was under my foot. And so I can sink. But if I do this, I don't give water the time to forget that it is here, because I hit it continually before it has forgotten. Okay? When I lift my foot, the water is still there. And when I put it down, it's still there. Now, that delta correlation corresponds to a decay of correlation that is short compared to the times in which you do your experiment. Of course, delta is a mathematical idealization. It's a mathematical idealization. There is no process in the world in which correlations decay instantaneously. But certain processes are so fast, I told you, no? Typical times of 10 to minus 12, 10 to minus 14 seconds, that for us are instantaneous. Okay? And this is the idea that Einstein had in mind when he developed this theory of the Brownian motion. okay, where you have pollen suspended in water, and the single grains of pollen get hit by the molecules of water continually over time scales that are much shorter than the pollen reaction to those kicks. Okay, so you can imagine the pollen velocity obeys a Langevin, very simple Langevin equation that is like this. V dot equals minus gamma V, which is the application of Stokes' law for fluids. You have a viscosity that goes inside the coefficient gamma, okay? And then V dot minus gamma V gives you the effect of viscosity. Viscosity will slow you down. If you put, you know, a small object, floating object into water, you give it a push, then after a while it stops. Why? Because viscosity of the fluid subtracts its energy. Certain fluids are more viscous than others. There are viscous fluids that I like very much, like honey. Honey is much more viscous than water. Water sometimes looks to have almost no viscosity, okay? But it does. It does have. It has a small viscosity compared to honey. This is the systematic part. In this case, okay, h of zt is minus gamma v, where gamma is a constant, plus, okay, some other constant that multiplies a gamma of t with these properties. Okay? Now, is it a valid approximation? Yes, it is a valid approximation under many, many, many circumstances to a very good degree of accuracy, because the molecules of water are something like 10 to minus 16 in mass than a pollen grain. Okay? You need 10 to the 16 molecules of water to move, to make the same mass of a pollen grain. And molecules move very, very fast compared to pollen. Pollen you can follow on a microscope. Okay? It was proven, this model of pollen was written in this form by Langevin following Einstein's prescriptions. And then, what do you do in a process like this? In a process like this, it makes no sense to solve the equation for each single pollen grain. Because you take this pollen grain, and in 5 minutes you find it here, and another pollen grain, in 5 minutes you find it there. If you repeat the experiments tomorrow, they go in totally different things. So you learn nothing from solving directly the equation, even if you could, which is not trivial. So you treat this problem stochastically, probabilistically. And now you want to know what is the probability of finding a pollen grain within a certain region. And that takes you to this. But this sort of equation is one of the good ones. Okay? It has that, it falls in that case. And then it is an equation that can be solved. And what do we know? And this you find it explicitly computed, for instance, in the book of Risken that I mentioned to you, but also in the book of Gardiner. Risken is a book directly on the Fokker-Planck equation, which is what you get from Kramers-Moyal when you stop at 2. And Gardiner is another book that does this kind of calculations, so you can see what you prefer. Now, what we know is the following, is that for such a process like a Langevin equation, dk Yes, thank you. Decay of zt is the limit that we wanted to consider. Limit tau goes to 0 of 1 over k factorial mk of z t and tau divided by tau. Okay? We need only 2, because Pavula will tell us that we stop at n equal 2. And so, if you call decay this thing, what we have for the Langevin equation is that d1 of z and t is equal to h of z and t plus g prime, the derivative of g with respect to z, g prime of z and t that multiplies g of z and t. And d2 of z and t is equal to g squared. So in the case of the Langevin equation for the Brownian motion, it's very simple. Okay? It is very simple because h is minus gamma v. And g is a constant. Okay? Right. G is a constant, so its derivative is 0. And then g squared will be the square of this q. So the Fokker-Planck equation is the equation for the probability evolution of this stochastic process. Now is a soluble equation. dw by dt is equal to minus d by dz of d1 of z and t times w of z and t plus d squared by dz squared of d2 of z and t times w of z and t. And then now the equation is easy or difficult to solve depending. Did I write right? I hope. Yeah, it is a partial differential equation. It is easy or difficult depending on the D1 and D2 what they are. In this case, of course, it is very simple. So I just give you the solution, and in my notes you see how you can get it. In particular, the stationary solution to which you converge in time, and it is proven that you converge in time. So where dw by dt is 0 is the famous Maxwell-Boltzmann distribution. Okay, this is a stationary solution to which you actually converge, and its form is like this for this equation. Okay, it is probability density of velocity is our W. Okay, as a function of velocity in one dimension is square root of the mass of pollen divided by 2 pi kb, which is Boltzmann constant, times t, e to minus m v squared divided by kbt. Now, this divided by kBt comes through Avogadro's number, which is the scientist from Turin, Avogadro. I would stop here even if I could go a little longer, but I think this is enough, and so we have a little more. And also in the second hour, I try to make it shorter so you have a little more time, because otherwise today is the end. Okay? If you have questions, after. In the last hour, I'll give you room to questions. Okay? See you later. What time do we reconvene, Sivaraji? 12:10. 12:05. 12:05. It is a short break, but it is for a good cause.